Get your dream on, let's talk about Riemann. All right, now, we've already discussed Darboux integrability in the previous video. Now we're going to discuss something slightly different, okay, Riemann integrability. Now, suppose f is a function. It's defined on the interval from a to b. That's been how we've been doing stuff so far. Now what we do is we suppose for any positive epsilon, there is a delta, so that for any partition whose norm is less than delta and any choice of sample points, we get the following inequality. Then we say the function is Riemann integrable on the interval, and that L is the value. Now this definition, it's a bit of a mouthful, but it's sort of familiar in its structure to definitions we've worked with before. It starts off with the same for any epsilon which is positive, and our goal is to force the distance between two numbers to be less than epsilon. Now L is this desired limit, okay, and we'll address what limit that is. What's this? The Riemann sum of a function with a partition and a set of sample points. Which partitions? There has to be some delta so that no matter what partition you take, provided the partition is fairly fine. Remember, if the norm is less than delta, every piece of the partition is shorter than delta. It is a relatively fine partition, especially if delta is very small. However, we want this to hold for any choice of sample points. It shouldn't be a matter of picking your sample points in a lucky manner. It should be irrelevant how you pick them. Provided your partition is rather fine, for any way of picking sample points, left endpoint, right endpoint, randomly, doesn't matter. If you can force Riemann sums to be this close to L, that's what it means to be integrable in the Riemann sense. So for some people, the fact that Riemann sums actually involve plugging numbers into a function makes more sense. But it is true that now you have to worry about how you're picking sampling points, and that adds sort of an extra layer of ambiguity into the process. This is why I prefer to present Darboux integrability first, because sampling points are just irrelevant. The trade-off is that you have to worry about supremums and infimums, and those are a little less easy to nail down sometimes. So here's an example, okay? A constant function is Riemann integrable, and the value of the integral is given by the constant times the length of the interval. Notice this is exactly the same value as the Darboux integral, okay? But we're using a different definition, so we've really got to do this. Now, for any choice of sampling points, regardless of the norm of the partition, f of every point is just c. Okay, so for any Riemann sum, this f of si, f of the sampling point, is just going to be a constant which I can factor out, and then the sum of the lengths of the pieces is always b minus a. So for any partition and any sampling points, the Riemann sum is exactly this value. And the picture, it's always awkward to draw constant functions, but if we have an interval, a to b, and here's our air quotes constant function, doesn't matter how you break it up, and it doesn't matter how you choose your sampling points, f of si is always just that constant. So when you take your Riemann sum, you're really just getting the same sum every time. Which means that if this is our choice of L, then it doesn't actually matter what the norm of the partition is. The distance from the Riemann sum for any choice of sampling points to that number L is 0, which is less than epsilon. So for any epsilon and any delta, you're always going to get the distance from your Riemann sum to this L to be less than epsilon. So the definition just falls right out. Yeah, the simplest functions we could possibly construct are integrable. It's not the biggest victory in the world, but we'll take it. Now here's another example of a function, the indicator function of the rationals. It wasn't Darboux integrable, and we claim it's also not Riemann integrable. So for any partition, okay, remember that to be Riemann integrable, the Riemann sums have to be within epsilon of some number, where that number isn't changing, but the sampling points are arbitrary. But if I pick sampling points to be irrational versus picking sampling points to be rational, I'm going to see very different behavior for the Riemann sums. So if I pick sampling points, which are irrational, my function's always spitting out a 0, and then my Riemann sum is always 0. But if I pick sampling points that are always rational, my Riemann sum is always spitting out 1s, and these delta xi's then add up to be the length of the interval b minus a. And the picture, again, and this is a very difficult function to try to draw, but here's my interval from a to b. It doesn't matter what partition I pick. On the one hand, and I'll use one color, I can pick rational sampling points because every interval has rational values, so I'm picking these to be rational. But on the other hand, I could have picked sampling points to be irrational, and since every partition has irrational values, I can always pick them to be irrational as well. Now the irrational values are going to evaluate to 0, okay, but the rational values are going to evaluate to 1, and therefore I'm going to see very different values for my Riemann sums. And if they're different depending on how you pick your sampling points, not just slightly different, but very different, then you can't have this property that the Riemann sum value doesn't really depend on the choice of sample points, and then you can't be Riemann integrable. So pick any epsilon in between 0 and b minus a. So there's no delta, so that if you pick a partition less than delta and any choice of sampling points, you can guarantee the Riemann sum to be within epsilon of any number, because either the Riemann sum can be forced to be 0, or it can be forced to be b minus a, and therefore I can't be within epsilon of both numbers. And again, the jumpiness, the fact that this function goes up and down between 0 and 1 so bizarrely between rational and irrational numbers, in Darboux discussions meant the supremum and infimum were always kept apart. And here it means it's possible to pick sampling points that yield very different Riemann sums. Yes. And this is true. We did show a while back that you can pick sampling points so that the Riemann sum is as close as you want to the upper sum of that particular partition, which means you can pick sampling points so that the Riemann sum is as close as you want to the supremum of all possible upper sums of all partitions less than delta. So in other words, there isn't that big of a distinction between these two ideas. Well, if there's not that much of a distinction between the two ideas, let's be formal about it. A function is Darboux integrable on an interval if and only if it's Riemann integrable, and if it is integrable in either sense, the value of the two integrals are the same. So these two notions of integrability are logically equivalent and produce the same values. Which means if you're trying to show a function is integrable or not, you can use either definition you want. You'll get the same answer, and proving it for one of them will automatically prove it for the other. And there will be examples where Darboux integrals with their sups and infs are actually easier to talk about than the concreteness of the Riemann sums. It will vary from problem to problem. The good news is, pick whichever you prefer. Once we establish this theorem, it won't matter. But we do have to prove this theorem first. So, suppose the function is Darboux integrable, and the value of the Darboux integral is L. Okay. First we need to show, then it is Riemann integrable with the same value. Then we'll have to go the other way, but for now, if it's Darboux integrable, then it is Riemann integrable. So let epsilon be positive. We're trying to show that f is Riemann integrable, but we know it's Darboux integrable. So with epsilon fixed, I know that the functions L of delta and U of delta have limit L. So since my two functions, L of delta and U of delta, have limit L, with any epsilon I pick, there must be a corresponding delta, so that as my delta prime shrinks towards 0, L of delta and U of delta prime are within epsilon of L. In other words, they are in between L minus epsilon and L plus epsilon, but they do always obey this inequality here as well. Now pick any partition you want whose norm is also that small enough so that L of delta prime and U of delta prime are both in between L minus epsilon and L plus epsilon. What we know is that Riemann sums are always in between upper and lower sums for that particular partition. But since the norm of the partition is less than delta prime, the lower sum for this partition can't be smaller than the infimum of all lower sums of all partitions whose norm is less than delta prime, whatever. Similarly, the Riemann sum for this one particular partition, regardless of how you pick sampling points, can't be bigger than the upper sum of that partition, and the upper sum of that partition can't be bigger than the supremum of all upper sums of all partitions whose norm is less than delta prime. So we get this chain of inequalities, and now we have a sort of squeezing going on. Since L of delta prime is bigger than L minus epsilon and U of delta prime is less than L plus epsilon, we get to conclude something rather nice. Okay. Basically, picture-wise, what's going on here is here's my function from A to B. Here's my curve. Okay. I know that if I make my partition sufficiently fine, then if I construct upper sums like this using supremums on each interval, so this is now constructing the upper sum for the function and this particular partition. Now I'm going to compare it to constructing lower sums by using the infimum on each interval. Not B, sorry, P. Okay, now compare that to a Riemann sum where we actually pick sampling points. Now the function evaluated at any sample point you want is in between the sup and the inf. So the Riemann sum overall can't be bigger than the upper sum, but it can't be bigger than the lower sum. I'm being a little lazy with my notation. But since the norm of this partition was less than delta prime, the upper sum of this partition can't be any larger than the upper sum, the supremum of all upper sums of all partitions whose norm is less than delta prime. And similarly, the lower sum can't go below the infimum. But we also established that U of delta prime isn't bigger than L plus epsilon, and L of delta prime isn't smaller than L minus epsilon. So if I just extract a few chains out of this links out of this chain, I should say, then what do we get? L minus epsilon is less than or equal to the Riemann sum for any choice of sampling points and any partition whose norm is less than delta prime. And that's how we're going to finish this proof off. And I should have mentioned that that does conclude the proof, that Darboux integrability implies Riemann integrability. We were able to force the Riemann sum, regardless of choice of sample points, to be within epsilon of L, provided that the norm of the partition was less than some delta, and that's the definition of Riemann integrability. So now we can start going the other way. Assume that the function is Riemann integrable. Let's show that implies Darboux integrable. So we want to show the function is Darboux integrable with value L. So we need to show that these functions, L of delta and U of delta, have the same limit, and they both have limit L. We know they have limits, we just need to show they have the same limit and it's L. So let epsilon be arbitrary. Because the function is Riemann integrable, there is some delta, so that regardless of which partition you pick, provided the norm is less than delta, and regardless of which sampling points you pick, the Riemann sum is within epsilon over 2 of L. We're using epsilon over 2 because we're going to add some more stuff to it later, but epsilon over 2 is still positive. And since the function is Riemann integrable, for any positive number, such as epsilon over 2, there will be a corresponding delta, so that for any partition whose norm is that small and any choice of sampling points, the distance to L is less than that value. But we have established in the past, for any particular partition, okay, such as this one, P, which was an arbitrary partition whose norm is less than delta, but now it's not changing, it's just some partition. We know it's possible to pick sampling points so that the Riemann sum is within any positive amount we want, such as epsilon over 2, from the upper sum. Okay. Now, if I combine this line with this line, the Riemann sum is no more than epsilon over 2 away from L, and the Riemann sum is no more than epsilon over 2 away from this upper sum. We conclude that the upper sum is no more than epsilon away from L, using a geometrically named inequality, the triangle inequality. Okay. You can cut out the middleman of the Riemann sum and directly compare the upper sum to L, and the distance is no more than this sum of these two, which is epsilon. But this was for any partition you want. The upper sum is never more than epsilon away from L, then the supremum of all possible upper sums can't be more than epsilon away from L. In other words, U of delta is no more than epsilon away from L. The same argument applied to lower sums tells us that L of delta is no more than epsilon away from L. This should be a strictly less than. And we've used that fact. Riemann sums can be forced close to upper and lower sums, which means if the Riemann sums are close to L, because the function was assumed to be Riemann integrable, then we can derive that upper and lower sums are close to L, and therefore so are U of delta and L of delta. And here's the argument. Yeah. Now, since U of delta and L of delta are both within epsilon of L, and again, this should be a strict inequality, it doesn't matter that much. Epsilon was arbitrary and delta was just small enough. As delta approaches 0, you must have that L is the value of this shared integral. There's no getting around it. And therefore, the function is Darboux integrable. So we have two equivalent definitions of integrability, but we haven't actually done that much with them. It's really nice that we've shown they're equivalent. If a function is integrable in one sense, it's integrable in the other, and the value of the integral doesn't change between the two definitions. So use whichever one you want. Unfortunately, the only function we've shown to be integrable is a constant. And the only function we've shown to not be integrable is that indicator function of the rationals. So we don't have a whole lot we can actually concretely work with yet. But if you think back to Calc 1, integrating functions wasn't hard at a certain point. I mean, you just did some stuff and you were done. Why are we being so circumspect about this? How do we start integrating things like exponential functions or sine and all that nonsense? It's going to take work. And yeah, I mean, we know how to integrate them, sort of. But the methods that you use in a Calc 1 class, try to think, if I said, what's the integral from 0 to 2 of x squared plus 1, the first thing you're going to do is try to anti-differentiate. And offhand, there's no reason these upper and lower sums or Riemann sums have anything to do with derivatives and antiderivatives. It's taking time to get there, but it will be worth it. Now, just as a heads up, we're going to put off integrating any particular function for a while. The reason being, we're going to collect some rules about integration. Remember, we have rules for derivatives like the sum law and the Leibniz rule or the product rule and the chain rule and stuff like that. And those are rules that tell us how to take derivatives of combinations of functions without being too particular about what function it is. Similarly, we're going to get rules about how to integrate sums of functions and which functions can be integrated on which intervals kind of stuff before we actually deal with any specific function. So for example, we're going to show that if two functions are both integrable on the same interval, then so is the sum. Okay, stuff like that. We'll also generate classes of functions that are integrable without actually integrating any particular function. For example, this is a big one that will come up later. If a function is monotone on an interval, then it is integrable. And that actually is going to be very, very important. It doesn't sound like you know examples of terribly many monotone functions, but trust me, that's a big part of your library. We'll get to that. But without actually putting a specific function in there, we're just going to generally show that monotone functions are integrable. And that's kind of what we're going to work on for a while before putting any particular function under consideration. The sort of crown jewel that we're working towards is the fundamental theorem of calculus, which links up the notion of integrating and anti-differentiating. And once we establish that, immediately, like a bolt of lightning, all the stuff you knew how to do in Calc 1 will suddenly be viable again. And that is the last thing we really get to here, because once you sort of turn that key, all of a sudden everything you already know is finally justified, and then there's no sense in going over it all again. So really what we're working towards is the fundamental theorem of calculus from this point forward. So ultimately, yeah, you already know how to integrate stuff, but you don't know why it works. And that is the purpose of this course typically, is to justify the why behind stuff you already know the how of. Now we introduced this notation, okay, for definite integrals, this scripty s symbol with a couple of numbers, and that's just a symbol. I mean, it happens to be an elongated s to represent its relation to Riemann sums, but whatever, it's just a symbol. But there's this dx in there. What does that mean, and is it important? So it can be a whole bunch of different things. In Calc 1, and in, for example, multivariable calculus at the undergrad level, it's really mostly a reminder to tell you what variable you are integrating. What is the variable of the function? Because you may have other constants floating around like a or b, and you want x to be the variable. There is a notion, however, of what's called a Riemann integral. My Dutch pronunciation is not good. Where you don't actually have a dx, you have a d and then a function of x, and it sort of represents a density function, where stuff counts more in certain places and counts less in other places. In Lebesgue integration theory, you don't put dx, you typically put d mu, where mu stands for your measure, but dx is typically used as shorthand for the standard Lebesgue measure. But if you want to change how stuff is measured, this is very similar to the previous notion. That's what the d whatever term is representing. And then more generally, in the theory of differential forms, dx is actually its own thing. D is the exterior derivative of the function x. And that's what it is. It's a legit thing that is multiplying f of x. In different contexts, these are slightly different meanings. They are all consistent with one another. Just like we showed Riemann and Darboux integrability give you the same value, it doesn't actually matter how you're interpreting it. You will generally get the same answers. There are, however, certain circumstances where one definition applies and another doesn't. It's not something we're really going to get into. For us, there's Riemann integrability and Darboux integrability, and we're only talking about real numbers. But there is kind of a handy shortcut. Since we're only talking about one very particular scenario, you can actually leave out the dx if it's really understood what the variable is. If your reader can be presumed to know the variable is x because it's really the only variable there, then you can actually leave it out. Back in Calc 1, 2, and 3, we yell at students and tell them don't leave this out. Our dirty secret is, once it's presumed everyone knows what the variable is, it's not the worst shorthand in the world. So why did we tell you not to do it? Well, in Calc 3, this is my reason at least, in Calc 3 in multivariable calculus, you're integrating against one variable and then the other, and then it's really important what order those come in. And so you need that notation there to help keep track. Okay, so now we've established Darboux and Riemann integrals are the same. But as I mentioned, coming up is just rules of integration to help build up what functions we know how to integrate.